So we talked about energy, we talked about all this other stuff. One thing we didn't talk about is time. It turns out that it takes depending on the arrangement, you can take a long period of time for a capacitor to charge up. It could take a short period of time. So we need to come up with an equation to best describe that. Now, when we talk about charge and the time it takes to take a full charge, let's use the proper notation on that one. Uppercase, Q, lowercase. Now, right there is the thing I should talk about. When we see uppercase Q, you're typically thinking of total charge. Lowercase q is typically talking about charge on a single capacitor. I mean, it could very well hold true for the entire the system, but typically lowercase q is referring to a single capacitor or a single type of charge. So the charge at a given amount of time, back to where we started, the charge for a given amount of time is equal to the maximum total charge. So the maximum charge that a capacitor could have, which you can then substitute as capacitance times voltage, but that's the maximum charge that it could have multiplied by 100%, or 1, minus e to the negative t over tau. Okay? So that's the equation for charging a capacitor. Okay? 100% minus whatever I haven't done yet. Okay? Now, t is just time, but tau is not. So tau has its own name. It's called tau for a reason because it's a step constant. It tells me how much it's going to charge. And as a matter of fact, we can relate tau 1/2 to a half-life. So it's a step constant. It tells me this is how much charge per second that I'm going to get, basically. Okay, so tau turns out to be the resistance times the capacitance. Okay? So if it's a single resistor problem with a single capacitor, it's the resistance times the capacitance. If it's the entire circuit, it's the total resistance times the capacitance. Or if it's a section of the circuit, it's the resistance in that section times the capacitance in that section. So that's tau. Okay? But if we want to refer to half-life, like we did in nuclear in nuclear physics, we can say T1/2 or tau 1/2. Okay? That's equal to, well, natural log of 2 times RC. Okay? So the half-life, the amount of time it takes to get half of the full charge into a capacitor, is equal to the natural log of 2 times RC. You could actually solve that mathematically by saying, well, 50%, 100%, solve for tau. And you'll end up with this natural log of 2 times tau. Okay? So that's the half-life for a circuit. Cool? Now, if you're talking about discharging and not charging, the equation is Q max times e to the negative t tau. The exact same equation, except we're removing this idea of 100%. We're talking about just this component. Okay, so this is discharging a circuit, this is charging a circuit. Okay? So that's the equations for the amount of time it takes to charge, let's say 75%, 85%, or 100%. Now the interesting thing about 100% is it'll never happen. When you look at nuclear decay, you never get 100% decay. You always get 99.995% decay. Never get 100 because mathematically it's not possible. You're taking a half of 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 a half. You go on infinite amount of times to get to 100. But for reality, 99%, that might as well be 100. Okay? Cool? So that's the amount of time it takes to charge a capacitor.